Hello everyone, I hope you're enjoying your break. I know I am, or at least I will be once I get to my break. Of course, I'm recording this beforehand, so anyway, I guess that's probably confusing. Let's talk about acids and bases. All right, so the concept that we want to start out with acids and bases is that of a hydrogen ion. Okay, so a hydrogen ion is a hydrogen atom that doesn't have any electrons. It's H plus. Um, that's the type of ion that hydrogen makes. When a water molecule loses a hydrogen ion, what's left behind when you take away one hydrogen ion from a water molecule is a hydroxide ion. So there are two important players when it comes to acids and bases, hydrogen ions and hydroxides ions. So that's OH minus for the hydroxide ion, and we're not actually showing it here, but H plus. Now, when this happens in water, when a water molecule loses a hydrogen ion to become the hydroxide, that hydrogen ion doesn't just float around in solution sort of unattached to anything. Usually it attaches itself to another water molecule to make this molecule right here, which is called the hydronium ion. Now, I don't use that term very much. A lot of times we'll simply talk about something losing a hydrogen ion and producing H plus and OH minus when water loses a hydrogen ion. But in reality, that hydrogen ion that gets lost from the water molecule attaches itself to another water molecule to make H3O plus. This is referred to as self-ionization because the only player here is water. This doesn't really happen very much in water, where one water molecule loses a hydrogen ion that gets picked up by another water molecule, but it does happen a little bit. Actually, it happens a lot more in other compounds. Specifically, lots of other compounds can lose hydrogen ions or actually also lose hydroxide ions, and that's the basis of acid-base chemistry. Okay, so first of all, with acid-base chemistry, we're always talking about solutions. This is chemistry. This is solution chemistry, where compounds dissolved in aqueous solution. All right, so a solution that has a lot of H plus, and that, let me give you a quick terminology here. This bracket, when you put brackets around something like this, that means that the concentration of, or in other words, how much H plus is dissolved in a solution. These brackets mean concentration. So a solution that has a high concentration of H plus is called an acid, and a solution that has a high concentration of OH minus, the hydroxide ion, is called a base. We sometimes also, or at least in the old days, they called bases alkaline solutions. There are some characteristics about acids and bases that you need to be familiar with, and they are listed here. Acids have a sour taste, but please don't taste things in the chemistry lab. Acids will change the color of a pH indicator paper, and we're going to get to pH in a minute. Acids will react with certain kinds of metals to release hydrogen gas, for example, with magnesium metal. We saw that in our reactions lab. Acids will react with bases to produce water and salt, a kind of salt. This is one of our reaction types. This is a double displacement reaction, a specific kind of double displacement reaction called a neutralization reaction. We didn't talk about neutralization reactions when we discussed reaction types because they're really just a subtype of double displacement. So an acid-base reaction is a neutralization where the acid and base neutralize each other, and that's really a double displacement reaction. And of course, acidic solutions conduct electricity. Contrast that with bases, where bases taste bitter, but again, please don't taste anything in the chemistry lab. They feel slippery, and they also conduct electricity. So there are some similarities and some differences in the characteristics between acids and bases. The main difference between them is that an acid is a solution where there's a lot of H plus, while a base is a solution that has a lot of OH minus. And that's what I'm kind of trying to show with this diagram here, where if there's an acid in an aqueous solution, you'll have a lot of H pluses around. And if it's a base that's in an aqueous solution, you've got a lot of OH minuses around. Now, if the concentration of H plus and OH minus are equal to one another, that's called neutral. All right, and On the pH scale, which of course I know you're all familiar with because you took biology. I know we teach pH in biology. I think we teach it even at the middle school level, so you're familiar with, or at least have heard of the concept of a pH scale. pH scale is a way to measure acidity or basicity of a solution. All right. Neutral on the pH scale is a pH of 7. All right, and as you go down the pH scale, 6, 5, 4, 3, 2, the solution becomes more acidic. As you go up the pH scale, 8, 9, 10, 11, and so on, it becomes more basic. All right, but if the two concentrations are equal, if the amount of H plus and the amount of OH minus are equal, then you say that solution is neutral. All right, so let's delve a little bit into this pH idea. Excuse me. Whoops, wrong way. This is an example of the pH scale. These little colored squares are just supposed to indicate that when you use a pH indicator, like a pH paper strip, which we'll be doing in class once we get back from our break, pH paper changes color to represent the pH. And here's our pH of neutral right here in the middle. It might be hard for you to see. That's a pH of 7. As you go down and the numbers get smaller, the solution is more and more acidic. There are more and more H plus ions around down here. And as you go up from a pH of 7, 8, 9, 10, 11, you get more and more basic. Yeah, it's a more basic solution, and you have more and more OH minus around. All right, and that's what we're trying to represent here. Now, this idea of pH, the pH of a solution is equal to the negative log of the hydrogen ion concentration, or the H plus concentration. So here's that in equation form. pH equals negative log base 10 of the H plus concentration. All right, and so when you have an acidic solution, like we are showing up here, you've got a lot of H plus around, and that means when you take the negative log of that H plus concentration, or the amount of hydrogen ions dissolved, you're going to get a number that's bigger than 7. Sorry, smaller than 7. So that backwards. So pH less than 7, it's acidic, and that means that there are lots and lots of H plus around. If the pH is neutral at 7.0, that's where the H plus ions and the OH minus ion concentrations are equal, and that actually is a pH of 7. And if you were to measure the actual H plus concentration, which we'll get to in the next unit, not in this one, you would find that the concentration of H plus is 1 times 10 to the minus 7th molar. Don't get too hung up on this part right now. Really, I want you to know this part right over here. pH greater than 7, over here, that's a basic solution. That actually means there's not very much H plus around, and instead you've got a lot of OH minus, a lot of hydroxide around. All right, so key piece here, pH is equal to the negative log of the H plus concentration. So if you were given the H plus concentration, you could calculate the pH. All right, we're going to delve into acid and base theories now, or in other words, chemical theories that describe what is an acid and what is a base. And there are 3 of these that you need to know. 3 guys, named for people who discovered them. The first guy is Arrhenius. Lived quite a long time ago, 1800s. His acid-base theory definition is that acids are hydrogen-containing compounds that can produce hydrogen ions in solution. Kind of like that figure that we had back where I had the little beaker of water that had a lot of H pluses in it. So Arrhenius said a very simple solution, or rather a very simple theory, that an acid is something that yields or gives off hydrogen ions, H plus ions. And then a base is something that releases hydroxide ions in solution. All right, so kind of a simple definition. Acid gives off H plus, base gives off OH minus. It's actually too narrow of a definition. It doesn't work very well, but it was a good starting point back in the day. Now, these 2 guys, Bronsted and Lowry, came up with another definition, a better definition for acids and bases. They said an acid, and it kind of sounds like the Arrhenius one, but it's a little more broad. An acid is something that gives off hydrogen ions. An acid is a hydrogen ion donor. It gives off or produces hydrogen ions. And a base, the definition is a little different. Here, the base is a hydrogen ion acceptor. Using the Bronsted-Lowry definition, you get more things designated as acids or bases. It's a broader definition, so it's better in that regard. So it doesn't say that a base is something that gives off OH minus. Instead, these guys say that a base is something that accepts hydrogen ions, H plus ions. And if you use this kind of definition, the Bronsted-Lowry definition is useful because of the concept of a conjugate acid-base pair. So let's take a look at this equation with a base and an acid that react with one another. All right, and our base in this case is ammonia, NH3. You'll notice that NH3 does not have an OH minus in it. This compound, NH3, can't give off OH minus. So Arrhenius definition would not call ammonia a base, but it is a base. So if ammonia reacts with water, it can produce NH4 plus, the ammonium ion, which we've run into this on our polyatomic charts before, and OH minus. So when ammonia and water react, you get NH4 plus and OH minus. So we like to label things in science. We like to have names for things. We call ammonia the base and water the acid in this case. And then we can introduce this idea of the terms conjugate acid and conjugate base. So the thing that was an acid over here is called a conjugate acid. I'm sorry, I said that backwards. Got to be careful. The thing that is a base here, which is ammonia, turns into a conjugate acid over here on the right side of the reaction. So NH3 accepts a proton, right? Accepts an H plus and becomes NH4 plus. And in doing so, it changes from a base into the conjugate acid. Similarly, the thing that is an acid here on the left side donates a proton and becomes the conjugate base on the other side. So that brings us to our definition. A conjugate acid-base pair, conjugate acid-base pair, two substances, ammonia and water in this case, related by the loss or gain of a single hydrogen ion. So what you really need to see here is that water is losing a hydrogen ion to become OH minus, and ammonia is picking up that hydrogen ion to become NH4 plus. And the terminology, so that we can kind of talk about them, is that ammonia is a base on the left side and a conjugate acid on the right. Water is an acid on the left side and a conjugate base on the right. Now this is just an example for ammonia and water. There are lots of other examples of conjugate acid-base pairs, and there are some in the book chapter that I'm asking you to read that goes along with this lecture. So you'll see other examples. All right, the third and final theory for acids and bases came from a guy named Lewis. He's the same guy that gave us our Lewis dot structures. So he was all about electrons. He said that an acid is a substance that can accept a pair of electrons and form a covalent bond. And a base is something that donates a pair of electrons and forms a covalent bond. This is by far the broadest definition of an acid or base, because there aren't any there's no requirement for hydrogen ions or for hydroxide ions. So the most things, this is the broadest possible definition that includes the most possible compounds as being characterized as acids or bases. We actually don't use this definition as much as we use the Bronsted-Lowry definition, but this one is more current, it's newer, and it's more broad. So here's a summarizing table of the theories for acids and bases: Arrhenius, Bronsted-Lowry, and Lewis, and it lays out what definition each of these three theories uses for acids and bases. So write this down. You're going to want to know this. And that's all we have for our acid and base notes. Thank you.